Hello guys, in this video we will be seeing an alternative approach for evaluating integrals within limits. So here there is a procedure which I learned from Professor Malai K. Das from IIT Kanpur. This is an NPTEL course applied numerical methods. So this is lecture 3. I will drop the video link in the description. You can see it. So what this approach is like. The first step is take a blackboard and draw the function u of x. Here the black box is the blackboard and function u of x is represented by the blue line. So give a large number of chewing gums to kids and ask them to chew and throw the gums at the board randomly. And the only condition that is given is the chewing gum should land within the limits of the board, within the black border. That is the only condition. And third step is count the number of gums in and out of the drawn area. Here the blue dots represent the gums which is inside the function u of x, and the green dots represent the chewing gums which is outside the function, which is away from the blue line but within the blackboard. So we have to evaluate integrals using this ratio, that is area of blackboard multiplied by the number of chewing gums inside the curve divided by the total number of chewing gums. So this gives us a ratio of what is inside the area, and when we multiply the ratio to the total area, that gives us a close approximation of what is inside the area within the curve. Okay, so that is a close approximation, and since this is a numerical method procedure, we cannot expect exact answer. So this method is followed to evaluate integral of 0 to pi sin x dx. So this is the program which he has proposed to find the or calculate the close approximation value for this integral. Analytically the answer is 2, and he says that this program should give a value which is very close to this. So I opened up a Jupyter Pi notebook and wrote this code for evaluating 0 to pi sin x dx integrals, and I imported all the uh, libraries and did the exact same code with the exact same variables. And as we could see, it uses the function random, which means every time we are going to run this code, we will get a different answer, but it will be close to the analytical value, which is 2. In this case, he has got a value which is around 2.0006, but we are getting a value slightly higher than that. But if we run again, we are getting something less than 2. I'm going to run again. Here again we are going to get some other value, and at some point in this video he says according to the theory of probability, the maximum number of values which will be coming as output should be more or less close to 2. So because that is the analytical value, so by probability and stochastic method, the most number of occurring values should be around 2. So how to check that? For that I am going to take uh, matplot library. So I am going to, and I am going to introduce one more array. So array as 0, and I am going to take a while loop. So let me run the case for around 1000 samples. Or initially we'll take 100 samples. I will take n sum, meaning n sample. So I'm going to put this whole code inside that function. So for no, I'll use while loop. While n sum is greater than 0, I'll run this code, and every time the loop runs, I will reduce n sum by one value minus equal to 1. But there is one problem. While we are using while loop, this j equal to 0 should be declared inside the while loop so that it gets initiated within the while loop, or else it is going to calculate j over and over again, and instead of coming back to 0 for every 100,000 values. So I am not going to print ifx here. So once this is calculated, I'm going to append the value, that is the ifx value, into this array. So how do I do it? Array dot append ifx. Okay, now if I just output array, we can see there are about 100 values which are more or less close to 2. So I'm going to plot this using histogram. How do I do it? I'll use matplotlib, which is like lt dot hist of array. So after I give run, I have to wait for a few times. If you see here, the maximum number of value is about 2, and it is almost equal to 2.005. But this is for a very small sample. So let me increase the sample. After I increase the sample, it is going to take some more extra time. Now if you see, it is very high in the 2. That is what we actually expect. And for one last time, let me increase it to 1000, because beyond that it is going to take much more higher number of iterations, hence large number of time. Okay, now if you see, the value is almost more or less same as 2. So that is what we actually expect, and the other values which are slightly far away from 2 is also very less. So if you run it for more and more samples, it is going to converge to 2, obviously. So that is what happens. And if you want to see the code, I will drop the code in the description box. You can see it. I'll give the GitHub library. But after a lot of lectures, he says that it is an exercise to evaluate sine x square. I mean x square sine x. I don't know where the slide is. So we have to evaluate for x square sine of x, and that is what I am going to do. So we are going to do for x square sine of x. So everything is same here, but here the x value ranges will be different. So it will be 0 to pi, but y value will be changing. That is, if you see analytically, the answer is about 5.8. So we actually don't need 0 to 1. Instead we need up to 6. So just rd.random is going to generate values 0 to 1, random values. But if I multiply by 6, it is going to generate 0 to 6. So that is what we want. Also in the f of x, the function is going to change slightly, which will be x square into the function. Also the area which we are plotting will be different also, because in this the integral of f of x is using the ratio, which is j divided by n, which is the number of chewing gums within the curve to the total number of chewing gums, multiplied by the whole area. But here the area is just pi, because it is pi by 1. The x-axis is 0 to pi and y-axis is 0 to 1. So if you take the magnitude, it is pi into 1, but here we need 6 into pi. So I'll just multiply 6 here, and I'm going to run it again, maybe for just 10 iterations. And if you see, the actual value is about 5.8, and the value is also slightly higher here, but it is also more over here. So let me take 100 iterations and I will run it. Now if you see, it is more and more close to the actual value. If I take 500 last time, So we can take it as a very good approximation that the value is about 5.87 or 5.86, where the histogram is very high. So that is how this method works, and this is sort of Monte Carlo method. So that is what he says, and if you have any doubts, you can just drop it down in the comment section. And if you like this video, give it a thumbs up and subscribe to the channel for more videos related to mathematical modeling and CFD. Thank you.